so let's take a look at this here. We have our three-dimensional space that's defined with 3 axes instead of just 2. Now, depending on what book you read or whatever, you may see the axes laid out a little bit differently. Okay? Sometimes they'll have X over here and Y coming towards you and Z. Pretty much all of them have Z going straight up. But you may see some variation. It's really just an issue of perspective. Okay? But we'll look at it this way. We want to, there we go. What we want to do is kind of define this three-dimensional space that we're graphing in, look at our axes, how they're drawn, and then just do a little bit of practice actually drawing these, okay? And the one thing that you need to do is make sure you pay close attention to just to the coordinates themselves, so you don't make certain assumptions. Like, it's possible that 2 points look like they're right next to each other when one is kind of in the foreground and one is way in the background. So you have to pay attention to the coordinates. So, first of all, notice we draw this z-axis vertically. The x-axis is kind of coming out towards us, and the y-axis is kind of going side to side, or left to right. We can call these planes here like YOZ. This is the plane going through the y-axis, through the z-axis, and hitting the origin. Okay. So we can define each of those different planes that way. But notice how we could then graph points. You're going to be given not an ordered pair, but now you're going to be given 3 coordinates to deal with, x, y, and z. And when you're sketching these, it's going to be important to kind of build your position. First of all, going off of your x-axis, all right, however far that is, okay? Then, what you want to do is you'll figure out how far over on your y you need to go. Let's say that that's y. Okay? And what you're going to do is take that length and move that far over from where you ended up. Okay? See that? That's how long y is. We're going to move from where we left off with the x's. Okay? Then we can do the same thing with the z. All right? Let's say our z coordinate takes us up this high. Okay? So, from where we left off here, we're going to go straight up, and then there's our point P. Okay? So that's like a quick illustration. Let's actually show you one of these in reality, how we would sketch it. Okay? Here's the point, 2, 3, negative 4. All right? So, notice I have my x, y, and z axes. So first I'm going to go a positive 2 in the x direction. So here's 1, 2. All right. Then I need to go a positive 3 in the y direction. So I'm going to mark 3 here. And you can just kind of measure. All right, there's my 3. And I'm going to go parallel to the y-axis. Don't go straight sideways, but go parallel with the y-axis from where x was 2. Now we have where y is 3. And then we have z equal to negative 4. So on the z-axis, here's 1, 2, 3, 4. There's a length of 4 on the z-axis. So I'm going to go straight down from there. Okay? Let me get another one of these. There we go. So I go straight down from there, and that means point P is going to be right there. Okay? So it's kind of out towards us with the x and y, but then it's down because the z was -4. Okay? So it can be a challenge. You just have to take your time with it and keep in terms of measuring along the axis and then also moving in a direction parallel to the axis that you're trying to get the coordinate of. Okay? Let's try another one here. Let's say 4, 5, 6. Alright? So, on the x-axis, 1, 2, 3, 4. Here's a length of 4. On the y-axis, we want 1, 2, 3, 4, 5. So here's our length of 5, and we're going to go from where we ended up. Notice again, parallel to the y-axis. And then finally for z, 1, 2, 3, 4, 5, 6 in the z direction. That's how far it should be. So I'm going to now move that or measure that from where I left off. And now we have our point P. Okay? So, it's a little bit of trying to visualize. Okay? You guys go into higher level calculus in college, you'll do multivariable calculus and you'll be graphing stuff on the three-dimensional plane a lot. Okay, you don't really do it too much until you get to multivariable, but
So you have like 3 variables there, or do you have more?
technically you could have as many as you want. Typically they stick to 3, but technically you could keep adding variables as long as you wanted to. But we like 3 because we can actually visualize it. So we're going to learn how to do integrals this year. You'll learn how to, if you take multivariable in college, you'll learn how to do double integrals and triple integrals with multiple variables. So
How is that? How is Z6 there?
we just measured up 1, 2, 3, 4, 5, 6, and that distance I measured from here. Yeah, that's where it kind of plays with your mind because you're like, oh, Z's only 2 there. Well, no, I'm coming from this spot up here, the same height. That's why I like to, you know, obviously you can't drag and drop on your paper, but you know, mark it off and then kind of use your fingers or a pencil tip or something like that to
That's
get
what I
the
wanted
distance.
to. Do we just eye it when we sketch it, or?
Yeah, and that's where like show that you're actually measuring it here. Show that you're actually measuring it, and then you can approximate it. Yeah. Okay. Does someone want to try to graph Q for us? All right.
Yeah.
Alright.
4. I'm confused with the 5.
Oh wait, why is it? I don't know how to use all these drag and drop things. I'm just gonna do it how I did it on my paper.
It's okay. All right. So there's your -5. Good. Great. Good. So what about the y?
I got it.
Did that make sense now? Good. All right, good. So we move 3 in the along the x-axis, then a -5. So we're going to the left there, and then we go up 1, and there's Q. And again, this is where you got to pay attention to the coordinates because it looks like Q is right on the y-axis, but we know it's not. It's just in our line of sight towards the y-axis. Okay? So you just got to be careful with that. All right, so there's graphing. Any questions? Okay. All right. messing with my text boxes. There we go. Alright, so next I want to look at our unit vectors, okay? You guys can, the ij, and then for the third dimension, see you guys, the third dimension is we incorporate this unit vector k. So if we have some position vector where p is a point, then we could have the vector x, y, z, or we could write it in unit vector form, x times I plus y times j plus z times k. Alright, so it's just the coordinate of the point, or the component of the vector, we should say, even more accurately, make it x I plus y j plus z k. So in this case, obviously we could write vector OP, if this is point P, 2, 3, negative 4, we could write it as 2, 3, negative 4, or we could also write it as 2i plus 3j minus 4k. Alright? Part of the reason why we use the I, J, and K is it actually does make operations with our vectors really easy. You guys saw this when we were doing it in 2 dimensions. You just combine like terms, essentially. You know, if we have a 2i plus 3j minus 4k, and then there's another vector that's 5i plus 4j plus 10k, just combine the i's, combine the j's, combine the k's, and you've got it. Okay? So, that's one nice thing about the component vector form, is it makes those operations a little more algebraic. You kind of can treat it like an algebra problem rather than a vector problem. So, if you like that. Alright, so those are our unit vectors. A unit vector, remember, by definition, again, has a magnitude of 1. If we wanted to, let's say, find C to make vector V a unit vector, okay, then, and we had, say, the vector 2, 1/3, and C, what do you think our formula might be?
Can you say Pythagorean theorem? Is that
It's not exactly the Pythagorean theorem because we're in 3 dimensions now, but it's
the same concept, like
exactly.
square root of 2 squared plus 1/3 squared plus 2 squared.
good. So, good, the magnitude of V is going to equal that. It's the same concept. That's the nice thing about this 3-dimensional stuff. A lot of the formulas are essentially the same, they just have this 3rd dimension component thrown in. Okay? So, I just made this up so it's not going to really turn out pretty, but that's okay. We want it to equal 1. So, I know that's 4, and that's 1/9. Okay? So 4 and 1/9 plus c squared has to equal 1. So I square both sides to get rid of the radical. And this is what I get for making stuff up, because we get c squared equal to a -3 and 1/9. So there's no solution, because it's imaginary. Alright? But anyways, that's the idea. Okay.
What's the usefulness of a unit vector? Seems like position vectors are more like, it's easier to find the magnitude and just like visualize it.
Well, what we could do, like let's say we had, I'll just get rid of this part.
Breaking down into one part of it, like
Well,
dividing it almost.
Exactly,
So you're like, so that way
actually.
you can add it.
If I did the magnitude of this vector OP, square root of 4 plus 9 plus 16, that'd be the square root of 29. If I then took 1 over the square root of 29 times vector OP,
It would give you like the next segment almost.
well, what that actually does, I'd have 2 over square root of 29, 3 over square root of 29, and negative 4 over square root of 29. So basically what we could do, and we'll talk about this more actually, but since you asked, we know that magnitude is 1. So that's basically a pure unit direction, unit vector in this direction. Now, let's say we wanted the magnitude to be 100. I have the unit vector.
Any magnitude.
Exactly.
In the same direction.
Yeah,
Okay.
same direction as this, but now if I want the magnitude to be 100, I just multiply that whole thing by 100.
So kind of like a conversion factor.
Yeah, it's kind of, it allows us to do conversions from one magnitude to another. So, and we will, like I said, we'll do some practice with that and whatnot in the future. So, now, again, similar process. We already talked about this magnitude, all right? But if we're trying to find the vector between 2 points, as we did when there were 2 dimensions, we take the coordinate of the point that we're going to and subtract the coordinate of the point we're coming from. All right? It's just now we have a z coordinate that we have to incorporate as well. Okay? So in this case, if I wanted to find vector AB, we'll go ahead and do it with this notation because it's a little easier with 3 to fit it all in. We're going to the point B. So I'm going to put the -3, the 2, and the 3 first. And then I'm going to subtract the coordinates of point A. So -1, -5, and minus a -2. So now we've got our vector AB, -4, -3, and 5. Okay, so again, same process that we used before, but we just had that third coordinate involved. If I want to graph this, there's, went too far. There's my 1. I want to go over here this same distance. So that is about this long here. Okay. And then I need to go down 2. So that's that distance. All right. So here's point A. And then for point B, I have a -3, a +2. So here's -3, here's a +2. So it's going to go out to here. And then a +3, so up 3. So that distance from there puts me here. Okay, so vector AB is that right there. Okay, and to do that, I'm going to have to go 4 units kind of backwards on the X, 3 units kind of towards the left on the Y, and 5 units up to get from A to B.
So it's almost like you have to like look at it from like a side angle, like you.
Yeah, it's really hard to visualize this on paper or on a board, but that's why a lot of times we just stick to looking at the components and the vectors and stuff rather than, and that's where computer assisted design has really done wonders, because now we're able to rotate things and get those different perspectives and see how things really relate to each other, rather than just, they used to design 3-dimensional things, which is blueprints, and they'd have to draw like a front view, side view, top view, to get the different perspectives. Now with the computers that can deal with these 3-dimensional graphs, you can spin it and rotate it and stuff, and it's really, really amazing. So, all right. So, that's all we're going to do with the vectors in space at the moment. Okay, we're going to be working more with 3-dimensional vectors in chapter 13. Basically, wait, did we completely finish, or do we have one more section? I think we have one more section. Yeah. We're going to be looking at how to do different operations with the vectors in space tomorrow, and we're going to spend a lot of time in class just practicing with those. And then 12J applies to both 2-dimensional and 3-dimensional ones, but we'll be done with chapter 12 by the end of the week here. Okay, the quiz on Thursday is only over 2-dimensional stuff.
So
Okay.
today isn't on it.
So today is not on there. All right.
Okay.
So